Welcome to Wednesday's class. Apologies, once again, we're having an online class today. We're just having kind of a chaotic few weeks here. My apologies again. Today we're going to be going over the last two sections before we do our review class tomorrow. Stay tuned on whether that one will be in class or online. Probably in class, let's hope so anyway. Today we're going to be going over how to solve rational equations, and then we're going to go over applications involving rational equations. So just remember, in our last class period we went over how to add and subtract rational equations. And to do that, remember, we found LCDs, we changed all our denominators into the LCDs, and then we went ahead and added, subtracted, and then we simplified and canceled if possible. Then we went over the complex rational equations. Remember, there were two methods to solve these. One involved treating the denominator and the numerator separately and just combining all the fractions contained in each one of those, and then treating it as a multiplication of two rational expressions, meaning you divide by the denominator. Or there was method two, that was my preferred method, and that was the method where you come up with an LCD for the entire complex rational, and so each and every denominator contained within, you come up with an LCD, and then you multiply that LCD by all terms. So that was the second method. So, simplifying the rationals and complex rationals, a lot of that is what's going to happen before we solve those rationals. So in this, so keep that in mind and do a little bit of practice before this lecture if you need to. Maybe just pause it and simplify a complex rational real quick, or just a plain rational. All right, so here are step-by-step instructions on how to solve rational equations. This is on the first page of the chapter, I believe. This says, and here's something that I usually forget to do in lectures and that I've been forgetting to do: list any restrictions that exist. Remember when we went through and defined restrictions to the domain or the inputs for these functions? Well, we got to do that on the first step usually. And those are numbers that would basically break big rules. The only big rule that we know of right now is you can't divide by 0. So then, after you do that, you list any restrictions that exist. Then you clear the equation of fractions. Right? We always want to clear fractions if possible. So after you clear all the fractions, then you just go about solving the equation like you would any other equation. Right? And so first off the bat, we list any restrictions. Second, we try and clear all fractions. So anyway, sorry, I interrupted myself there. List all your restrictions. Clear any fractions, then just solve it like a normal equation. Right? And so really the only difference between a rational equation and any other equation is those two first steps. You list restrictions, and then you clear fractions, and then it's just like any other equation. Let's do an example. So on this first example, first we list any restrictions that exist. Since there aren't any variables in the denominator, there's no way we can break any rules with this equation, right? Even if x equals 0 on the top, that just gives us 0 minus 0. It doesn't really break any big rules, so we don't have any restrictions. So let's go about clearing the fractions. We clear fractions by first listing all of the denominators. Then we write them out in prime factored form. And then we circle one, choose one, write it down. And then we fill that one in with any factors from the others that it's missing. So 12 completely contains 6, so that's good. 12 contains 2 factors of 8. But it's missing this last factor of 8, so I'm just going to multiply this by 2, and my LCD is equal to 24. So that 24 since we have an equation here and no longer an expression, we can actually kind of do this the easy way and just multiply 24 through by each and every term, right? In the past, I may have, or in expressions, I should say, maybe I would have converted all these denominators into 24. You know, I would have multiplied top and bottom of this first fraction by 4, and that would have created a 24 in the denominator. This second fraction, I would have multiplied top and bottom by 3. And this third, I would have multiplied top and bottom by 2. Since this is an equation, I'm allowed to actually just multiply each, I'm allowed to multiply each term by my LCD. So this gives me 24x over 6 minus 24x over 8 equals 24 over 12. And then in my next step, I'm going to go ahead and simplify all this. 24 over 6, that's equal to 4. So I have 4x on that first one. 24 over 8, that's equal to 3. So I have 3x for this second term. And then I have this equaling 24 over 12, and clearly that's just equal to 2. So now you can see, after I've cleared all the fractions, I just have a basic equation, right? The x is not squared, so I know that I don't have to factor this. I just solve it for x. 4x minus 3x, that's equal to a single x, and that's equal to, whoops, clearly x is equal to x. That's just equal to 2, and so that's the solution to this equation. So if we want to, we can go through and enter 2 in for x and make sure that it makes this equation a true statement. All right, so this next one, we handle this the exact same way. First off the bat, step 1, we list any restrictions that we have. Restrictions only happen when the denominator may be 0. So in this case, these two denominators, 3x and x, if x equals 5, that denominator is not 0. If x equals negative 500, that denominator is still not 0. The only way this denominator is ever 0 is if x equals 0. So we're just going to say up here, x cannot equal 0. That's our first step. Our second step is we want to clear all these fractions. So we're going to come up with an LCD. So we list our denominators, 3x and x, and then we just notice that 3x completely contains the other denominator already. Right? 3x, it contains x, and it contains a 3 on top of that. So 3x is our LCD. So I'm going to multiply every term by that LCD. Okay, so I have 3x times 2. And I kind of I like to do this middle step, even though it's a little bit tedious, but it really does help me to avoid making kind of a lot of small mistakes that can happen when you simplify these kinds of things. So yeah. All right, and then we have 3x times 10. All right, on my next step, I'm going to go through and simplify all this. The 3x's in the first term cancel, and I get a 2. The x's in the second term cancel, and I get a 3. And then in the third term, I just multiply that out, and so I get 30x. Okay, so I have 2 plus 3 equals 30x. That gives me 5 equals 30x, which of course tells me that x is equal to 5 over 30, which is equal to 1 over 6. All right, 1/6 is not equal, and so, okay, so I should explain this. Now that we've come down to our solution, right, this is going to be, now that we're restricting our values like we did in the beginning of the problem, now when we get to our solution, we have to make sure that solution is not a restricted value. If it is, that's not a solution. If it's not, then we're fine. So our solution was 1/6. Our restricted value was 0, so we're fine. 1/6 is a good solution to this problem. All right, here's another one. So this one, you might be tempted to try and solve this just directly right off the bat without dealing with the rational part, but just having one fraction in your equation makes it rational, so you might as well deal with it in the same way that we deal with these other equations. So right off the bat, step one, we're going to say, okay, we have a single variable in our denominator that cannot equal 0. X cannot equal 0. Okay, so clearly, since there's only one denominator, there's only one common denominator, and that denominator is x. So I'm going to multiply every single term in this equation by x. So when I multiply the first term, I get x squared. When I multiply into the second term, I get the x's cancel and I get just a plain old 6. And then when I multiply into the other side of the equation, I get negative 5x. All right, and so now we're in a situation, we've got a second degree equation, so we need to consolidate all this to one side and factor it to solve it. So I'm going to add 5x to both sides. That's going to give me x squared plus 5x plus 6. Okay, and that equals 0. Now I'm in a situation where I'm allowed to factor this in order to solve it. So go ahead and pause this and factor it on your own. Don't be slacking. We got a test coming up, guys. You need all the factoring help you can get. So pause this and factor it. And then after that, just to test your memory a little bit, remember, try and solve it. Come up with the solutions real quick before I go ahead and do this. Go ahead and pause it. Right? If you're still kind of hazy on how to come up with those solutions, man, you got to do some practice because that test is coming up. So, okay, I'm going to assume you guys all solved it, you knew how to factor it, and everything was perfect. So I'm going to go ahead and do this. So, right, we need two numbers that multiply to give us 6, but add to give us 5. Those numbers are 2 and 3. Right? And so the solutions of this are whatever would make this final equation true. Right? And so all this stuff on the left side equals 0 if x equaled a negative 2. That would make this first factor 0, thus rendering the entire polynomial 0. The same would be the case if x were to equal negative 3. So those are my two solutions. Now I got to check them with my restriction. And I shouldn't have called them solutions yet. My restriction was x cannot equal 0. These are fine with that, right? Negative 3 and negative 2 are not equal to 0, so these are both solutions to this particular equation. I can plug them back in to check my work. All right, let's do a few more examples. They're a little bit more expansive than that one. So, okay, so once again, I see this equation with fractions in it, so I know that I have to go through my rational equation steps. The first step is to see if there is any value which we need to restrict. Check out our denominators. If x equals 0, we're fine here because that doesn't give us a 0 in the denominator. The only thing that would mess us up is if x equaled a negative 2. That would give us a 0 in our denominators, and that would be no bueno. So x cannot equal negative 2 is what we're going to say right off the bat. Now we'll notice that both our denominators are the same. And so we just, our LCD is just that denominator. All we need to do is multiply through by that denominator, and then we can cancel everything. So let's go ahead and do that. Draw my arrow here. Okay, so I'm going to take x plus 2, and I'm going to multiply it by every single term. So I have 1, the first term, multiplied by x plus 2. Then I have that added with 3x multiplied by x plus 2. And that is equal to a negative 6 times x plus 2 all over x plus 2. Okay, so I can go through this, obviously, and cancel all my x plus 2's. And that's exactly what I wanted. Now I'm done with the rational equation. All I have is a plain old equation that I'm used to that I can just solve. Okay, so let's keep going. So I have the x plus 2 that just stays out front, this guy here. Then I have plus 3x, right, from this second term. And that is equal to a negative, whoops. Hopefully you guys caught me on that. I wrote down a negative 2 here because I was spacing out, because that's what I always do. Don't be like me. Okay, so now I have the negative 6 hanging out after I canceled my x plus 2's. Negative 6. Okay. So now there's no second degree term on these variables, right? There's no x squared, which means this is a simple isolate the x problem, right? Nowadays we're dealing with two sort of different solution types. One is the plain Jane one, which is what we're doing right now. It's a single degree. The other one is the one where we factor things and set those factors equal to 0. That's like the second degree solution type. But this is the first degree, so this is sort of the easy way. So we're going to combine our variables on this left side. That gives us 4x plus 2 equals negative 6. And then I subtract 2 from both sides to give me 4x is equal to negative 8. And clearly, that tells me that x is equal to negative 2. Aha! But we've got a problem here. We restricted negative 2 already. We said that can't happen. But x cannot equal negative 2. Exclamation point. So, what happens when this is the case? Well, if there's no other solution that's not restricted, we have to say no solutions. The exclamation points are optional. It just depends on how you're feeling that day. And as you can see, you can make mini exclamation points or very large. All right. Let's tackle another one of these guys. So here we are. This is a rational equation. So we know that we want to clear these fractions right off the bat. Sorry, I should say right off the bat, we actually want to restrict our values. So what can x not be equal to in this equation, right? What values of x would render this equation undefined? Well, if x were equal to plus 5 right here, or x were equal to negative 5 right here, then we'd have a 0 in the denominator, and we don't want that. So we're going to say up here, x cannot equal plus or minus 5. Now we're going to list our denominators on the side, right? We're going to handle this like any other rational equation, even though if you've taken a look at this guy, you already know what the common denominator is. So we have x minus 5, x plus 5, and then we have x squared minus 25, which what I was getting after earlier, if you saw how to factor out this x squared minus 25, you saw that it factors into x minus 5 and x plus 5, right? And so this one completely contains the other two denominators, and so that's my LCD. So I'm going to multiply each and every term by x minus 5 and x plus 5. Draw my little arrow. So my first term here, 3 over x minus 5, turns into 3 times x minus 5 times x plus 5. And I'm doing these kind of the long way, just so we can see what's happening here. All right, I'll multiply the second term by the LCD. So I get 1 times x minus 5, x plus 5. That's over x plus 5. All right, and then on the very last side here, I have 2 times x minus 5, x plus 5. And that's all over x squared minus 25. So now I'm going to go through, I'm going to cancel a bunch of stuff. So I can cancel my x minus 5s in this first term, and I end up with 3 times x plus 5. I can cancel my x plus 5s in the second term, and I end up with x minus 5. And then I cancel everything on this opposite side of the equals sign, which leaves me with just a plain old 2. Now, once again, I'm in the situation where I only have a first degree equation, so all I need to do is solve for x. These 5s, whoops, I almost forgot to distribute that 3 and canceled that 5 early. So I need to distribute my 3 first. That gives me 3x plus 15 plus x minus 5 equals 2, which gives me 4x plus 10 equals 2. 4x is equal to negative 8 again. And then I get x equals -2. Now, since -2 was not one of my original restricted values, remember I restricted plus and minus 5, x equals -2 is a solution to this problem. All right, last one. Here we go. Here is definitely an easy problem, only if you recognize this one thing, is that both these denominators match, right? And so we can multiply through by the LCD, which is just those denominators, right? And so if we multiplied everything by the LCD, x minus 1, then we would get x squared times x minus 1 over x minus 1 equals 1 over x minus 1. Oh, and we have an x minus 1 up top. And of course, these guys just end up canceling. So we get x squared equals 1. Go ahead and pause it and see if you can figure out how to solve this equation real quick. This is kind of a weird one. If you see this on an exam, I don't want you freezing up. I want you to know how to do this. So pause it and try and see if you knew how to solve this. If you didn't, pay close attention to what I'm about to do. It's not that hard. So since we have a second degree term, we know that we need to consolidate everything on one side of the equation and then factor. So we're going to subtract the 1 from both sides. That's going to give us x squared minus 1 equals 0. And this is a difference of squares problem. So we'll get x minus 1. Oops, not x minus x. X minus 1. X plus 1 equals 0. So the solutions to this are x equals plus and minus 1. Oh, hopefully you guys caught me in that I forgot to restrict my solutions in the first step. And if I did do that, this would have told me that x cannot equal a positive 1. So down here in my final solution, I'm just going to get rid of the positive 1 version of that, and I'm going to circle the negative 1 version. And that's that. So that's the chapter on rational equations. Really, like, just memorizing those first steps is going to do you a world of good. Restrict any values and then clear the fractions. Right? Clearing the fractions might sound easier than it actually is, but it's really not that bad once you realize you just got to multiply through by all the denominators. You know, if you can't find the LCD, just multiply all the denominators through, right? Like I know it's a lot more simplification, but that's okay to do. So for example, if I had x over 33, no, I don't want to say that. Let's say x over 33 plus y over, I don't know, 41x minus 3/22 equals 1 over 5. So if I was confused as to how to find the LCD for this one, honestly, I'd probably want to find it because this is going to be a big number. What I could do, this is sort of the brute force method, is I just multiply all the denominators together without finding any LCDs or anything like that. So I would say 33 times 41x times 22 times 5, and that would be my LCD. And by multiplying that big number through all these fractions, I would end up with a fractionless problem in the end. I'd have a lot more probably simplification and stuff to do, just because kind of that's what finding the LCD does for you. It sort of allows you to avoid any simplification later, but this brute force method will work no matter what. You know, you just are going to have to bear down and simplify it when you're done. Okay, let's talk about everybody's favorite subject in mathematics, and that is application problems. So I think I've given this speech before, but just remember that application problems are very formulaic. You know, they tend to be variable just kind of in the scenarios they bring up, but you know, in the setup and the solutions, they're all very formulaic. So in this chapter, we're going to be going over problems, word problems involving work, word problems involving motion, and word problems involving proportion. Keep this in mind that, you know, these are only portion, a part of the word problems that we're going to be studying for the next exam. We did a whole chapter on applications in the last, a whole section on applications in the last chapter. All right, let's go on. So problems involving work. So we have these two people, Brian and Reba. They're volunteering in a community garden. Brian can mulch the garden alone in 8 hours. Reba can mulch the garden alone in 10 hours. Why does it take her longer? Because this book is sexist. Just kidding. She can mulch the garden in 10 hours. I know why. It's probably because she's mulching the garden with quality, whereas he is not. All right, so how long will it take for the two of them working together to mulch the garden? So these work problems are classically like, it's just two people doing the same job in different amounts of time. And these work problems will want to know, well, how much does it take them if they're working together? How long does it take them? To solve these, we always just use the work principle. The work principle says, and this is my favorite one down here. You can use any of these that you want. This one for me is just the easiest to remember for whatever reason. I don't know why. The work principle says that if A is the time needed for A to complete the work alone, so if we're doing our example above, A would be the time it takes for Brian, which would be 8 hours. B is the time it takes for B to complete the work alone, so B would be the time it takes for Reba to mulch the garden, 10 hours. T, which is the time needed for both A and B to complete the work together. T is typically what you'll be solving for, but not always. So 1 over A plus 1 over B equals 1 over T. All right, we said A was Brian's time, which is 8 hours. So I have 1 over 8 plus B, which is Reba's time, 10 hours. So I have 1 over 10, and that is equal to 1 over T. T is the one that we haven't solved yet. All right, so here I am with a rational equation. What I need to do is multiply through by an LCD. I'm going to find that by listing all my denominators on the side and writing them in prime factored form. Circle 1, draw it out, and then fill it in with any factors that it's missing from the others. We're missing a factor of 5, and we're missing a factor of t. This is equal to 40t. All right, so I'm going to go ahead and multiply each term of this equation by 40t. All right, now I go through and I simplify, and I'm just going to erase my LCD work down here, just to give myself a little bit more room. All right, so now I'm going to go through and simplify everything. So 40 over 8, that's equal to 5. So I have 5t. 40 over 10, that's equal to 4. And then 40t over t, that's just equal to 40. All right, this is a this is a first degree equation, so I don't need to set everything equal to 0. I just need to solve for t. So I have 9t is equal to 40, and then I can divide both sides by 9, which gives me t is equal to 40 over 9. All right. One thing I forgot to do, of course I did, is restrict any values, right? Right off the bat, I should have said t cannot equal 0. That's what I should have said. Since my solution did not equal 0, we are good on that, but I'll just list it down here. T cannot equal 0. Okay. Let's do a motion problem. So the base equation that we solve motion problems with is this one here, d equals r times t, where r is rate and t is time. Other versions of this that mean the exact same thing are d equals s times t, Yeah, just equations like that, where S typically means speed in this case. Okay, so let's go ahead and do this problem about biking. So on her road bike, Olivia bikes 5 miles per hour faster than Jason does on his mountain bike. In the time it takes Olivia to travel 50 kilometers, Jason travels 40. Find the speed of each bicyclist. Okay. So for motion problems, I typically like to set up a table. Across the top of that table goes my general motion problem, which is d equals s times t, dst. Along the side, I put typically the two things that are in motion, or the two legs of somebody's journey. So I'm going to say Jason, Olivia. All right. So now I'm going to fill these in for whatever I can. So the problem tells us that we have a single number for distance, right? And that tells us, let's see now, in the time it takes Olivia to travel 50 kilometers, Jason travels 40, right? And so that's in the same time. So the next column that we want to fill out is, that's going to be our speed column. So we'll just notice real quick that speed was the actual overall question of the problem. So we're probably going to name one of these our variable. Let's just go ahead and call Jason's bike x. So the speed of Jason's bike is x. It tells us in the problem, that Olivia travels 5 kilometers per hour faster than Jason does. So we can call Olivia's speed x plus 5. And I'm going to erase this k here. Okay, so now when we come to the t column, we say, okay, how much time did it take them to do this? So the key here is that it says, in the time that it takes, which tells us this is the same time, right? So they travel different distances, different speeds, but it's the same time. So we're just going to call that, for now, we're going to call that capital T, the same time. So now we're going to use our d equals s times t equation, and we're going to manipulate that so we can solve for x. So we have d equals s, oops, here, let me redo this. So we have d equals s times t, right? So we have this equation for Jason. We also have this equation for Olivia. The key to understanding why we do this problem is that this t and this t are equal. So what we do is we solve each of these equations for t. So if I divide both sides by s here, I get t equals d over s, right? And the same over here, t equals d over s. So I have Olivia's t equals d over s, and I have Jason's t equals d over s. They both equal the same t. So I have Jason 40 over x. That's Jason's d over s. That is equal to capital T. Capital T is also equal to Olivia's d over s, which is 50 over x plus 5. Okay, now I have this equation with a t in the middle. I can just get rid of the t and solve the rest. So I have 40 over x equals 50 over x plus 5. And then I multiply all terms by the LCD. Since both these denominators are prime, the LCD is just those two denominators multiplied together. Okay, when I distribute into each term, I get 40x times x plus 5 over x. That is equal to 50x, x plus 5 over x plus 5. Now I go through and I cancel. And this gives me 40x plus 5 is equal to 50x. From here on out, I just solve for x. So I distribute my 40. I get 40x plus 5 times 40 is 200. And that's equal to 50x. Now I'm going to subtract my 40x from both sides. That gives me 200 is equal to 10x. Divide both sides by 10, and I get x equals 200 over 10, which is 20. All right, so Jason was going 20 miles per hour. Olivia was going kilometers per hour. So that's a motion problem. Moving on. Problems involving proportions. So here is our official proportion definition. Let's jump right into it and see how we should be using these. So for the proportion problem, one of the most common things you're going to see is the similar triangles. And for a proportion problem, basically we say similar triangles mean they have all the same angle measures. The side measures might not be the exact same, but the angle measures are, which means they're proportional to each other. One side is proportional to the other. So, in this problem, they want us to figure out what is z. How do we figure out what z is? So to figure that out, we just need to use our proportional problem, right? And so the z's counterpart side is 5 over here. And all we need to do is use the other counterpart sides to make a fraction and solve for this. So I'm going to say z over 5, because that's side for side, over 10 over 8, another side for side. Z over 5 is equal to 10 over 8. All right, if we multiply both sides by, let's just say 40, because that's 5 times 8, then we end up with, let's see now, 8z equals 2, right? 40 times 10, no, not 2, that's ridiculous. So, sorry, we had 50, jeez. Why did I say that? Well, let's see now, 10 times 40 over 8, well, 10 times 40 is 400, for 8 into 400 is 50, okay. So I have 8z equals 50. At least I think 8 into 400 is 50. I'm going to divide both sides by 8. And I'm going to get z is equal to 50 over 8, which is 25 over 4. All right, so the side z is equal to 25 over 4. Let's keep going with these. So the proportion formula is really great when we're dealing with ratios, especially ratios from blueprints to real life or maps to real life. Like, you know, when you look at the scale of a map, when it says, you know, one kilometer equals 1 inch on this chart or something like that, we're using scales and proportions for that. So this problem is saying, hey, look at this blueprint. This blueprint is, it's represented on a 2.5 inch to 10 foot scale. So 2.5 inches for every 10 foot span. 2.5 inches on the blueprint is equal to 10 feet in real life. So 2.5 over 10 is the proportion that we're using as our base. They want to know what's this question mark up here, right? If 2.5 spans the length of 10 feet, then what's the distance that spans the length of 12 feet? Well, we're going to call that x, and we're going to solve for that. So we have 10 and 12 as our two denominators. We're going to find an LCD. I'm going to circle one of these, 2 times 2 times 3. I'm going to multiply in the factor it's missing. So that gives me 60. All right, so I multiply everything in here by 60, and that gives me 60 over 10, so that's 2.5 times 6, and that's equal to 60 over 12, which is 5x. All right, 2.5 times 6 is 15, I think. I don't have a calculator, so we'll just assume it is because I don't want to do the math on that. And then if we divide both sides by 5, we end up with x equals 15 over 5, which is equal to 3. Okay, so x equals 3 is the solution of this. So 3 inches up here is what we'd be looking at on the blueprint. Okay, here is one more proportions example. So this says Brent sent or received 384 messages in 8 days. That was his rate. At this rate, how many text messages would he send or receive in 30 days? So they're saying that his text messaging is going to be proportional. So he sent 384 in 8 days. And they're asking how many would he send in 30 days. So we just solve for x here. So what is the LCD between 8 and 30? Well, I'm just going to circle one of these and fill it in with any factors that it is missing from the other factorization. This is missing 2 factors of 2. So I have 8 times 3, 24 times 5, which is just a bunch of numbers. $120. Multiply both sides by 120. 120 over 8 is 15. So I have 384 times 15. And that is equal to 120 over 3, which is equal to 4. 4x. All right. So now I have 384 times 15. Let's see now, do I have a calculator available? No. I'm going to have to pause this and actually go get a calculator. Okay, I have retrieved my calculator, and it turns out that 384 times 15 over 4 is equal to 1440. So this dude sends a lot of messages in 1 month, maybe too many. I think he probably needs some hobbies or something. All right, so that is that on our application section. We'll be having a review class tomorrow, and then on to the exam. Just make sure that you're coming up to see Bethany on a regular basis. If you need some extra help, talk to your classmates about, how they understand the problems. And of course, email me, any specific problems you might have. I can work up some worked examples for you. So anyway, I hope you guys have a good day, and we will see you soon.